Hello everyone. In this video, we're going to be looking at problem number 9 in the exercise section of homework 1. And this problem focuses on normalizing a couple wave functions. First, we're normalizing sine of n pi x over L from these boundaries, a constant from these boundaries, and then e to the minus r over a and r times e to the minus r over 2a, both in three-dimensional space. But let's go in order and start just with the first one. So this problem we actually already did in, what number was this? Exercise 711? Problem 7. So for my 9th edition, I have it was solved in 711 or 7.11b. Yeah, that's problem number 7. So in these homeworks, you're allowed to reference your previous work since you've already done it. So you can just say, the following problem was already solved. See exercise 7. And then you can write the result. Since you already did it, you know that n is going to equal root 2 over L. And plugging that back into psi, we get psi equals root 2 over L sine n pi x over L. And that's your normalized wave function. Already done. Easy. Now, next. So we have psi as a constant in this part. So we can just interpret that as psi equals c. And c can just be any constant. And we're given a range. Range negative L to L. Now, if we remember our normalizing integral, we have n squared integrate from our given bounds, negative L to L, psi squared dx equals 1. So from here, we can plug in psi, n squared from negative L to L of c squared dx equals 1. And because this is a constant, if you remember from calculus, you can pull out any constant from an integral. And next we have n squared c squared from negative L to L dx equals 1. Now the integral of just dx is x. So this is nice and easy. We have n squared times c squared times x from negative L to L equals 1. Next step, just plug in our L's to subtract in this x. So we have n squared c squared L minus a negative L is just plus L equals 1. Simplifying, n squared c squared times 2L equals 1. And solving for n, we get n equals square root of 1 over 2 times L times c squared, which we can get rid of this whole big square root and just put it in the denominator and get 1 over c root 2L. So this is our normalization constant. And if we plug this back into psi, which is c, you can see that these two c's cancel each other. So psi just becomes 1 over root 2L. I'll box the normalization constants. Should have done that. So for A, we have root 2 over L, gives us psi given here. And then for B, we have this normalization constant that gives us this psi. All right, so now we're going to be looking at part C, which has us looking at a wave function of e to the minus r over a and 3D or in 3D space. And I don't know if the 11th edition has this. It honestly should. I don't know, but I'm gonna write it down anyway because this was really helpful to me. So when we integrate in over 3D space, that means we need to integrate with respect to tau. And Atkins writes it like this: r squared sine of theta dr d theta d phi. I like to see it better as r squared dr sine theta d theta d phi, because this represents a triple integral. So you would be, when you would be integrating over 3D space, what you have is, oh, and it gives bounds too. For r, it says this in the hint, but for r, you have from 0 to infinity. For theta, you have 0 to pi, and then from phi, you have from 0 to pi, to 2 pi. And so the triple integral will look like this. So if you have 0 to infinity, 0 to pi, 0 to 2 pi, psi squared d tau. Then you could break this up and plug this in. So in the end, you're getting 3 integrals, and these bounds correspond to the respective, I guess, parts of space that you're integrating. Okay, with that, we can move on to part C, because that's where this begins. So, first, remembering our normalization integral, we have n squared psi squared d tau equals 1. So from here, we can plug in our psi, since we know it. N squared e to the minus 2r over a d tau equals 1. And now we can substitute in this tau for these parts of the integral and break this up into 3 respective integrals. So from here, we're going to have n squared integrate from 0 to infinity, and we're going to multiply the wave function by r squared. So r squared times e to the minus 2r over a dr, integrate from 0 to pi sine theta d theta, and then integrate from 0 to 2 pi d phi, and all of this is going to equal 1. So now we can just break up these 3 integrals and solve them individually and multiply them together in the end. So first, we can look at this integral, since it's the most difficult. And in your essential integrals answers, it should be in the front cover of your textbook. It already solves this integral for you as a series, and it gives the series generally. So that solution is from 0 to infinity of x to the n times e to the minus ax dx equals n factorial over a to the n plus 1. And because these have the same form, basically what we can do is substitute in values for the solution that make it look like this. And if we can do that, then we can just plug in here and we'll get a value for that. So for this, looking here, we have x equals r. And for our n, we have n equals 2. And for our a, Here we have 2 over a. So we're substituting 2 over a. You can see that. We already have x as r, so that's taken care of. So now that we have these substitutions that make these integrals look the same, we can plug in our new values for this solution. And so from this we get integral from 0 to infinity r squared e to the minus 2r over a dr equals, so our n is 2, so we have 2 factorial over a is 2 over a times, or to the n plus 1, so that's 3. Simplifying this, it becomes 2a cubed over 8, which becomes a to the cubed over 4, excuse me. So this integral is solved. Check, done this part. So now we can do the second integral, and we have integrate from 0 to pi sine theta d theta, which equals 2. It's a good calculator, or you can just plug it right into the calculator. And then finally, the third integral from 0 to 2 pi of d phi just equals 2 pi. So now we're good. Integral 1, integral 2, integral 3. Now all we have to do is just plug those back in and simplify. So we get n squared times a cubed over 4 times 2 pi equals 1. Simplifying this, I will come down here. We get n squared a cubed pi equals 1. And then solving for n, we get n equals square root of 1 over a cubed times pi. And we can plug this back into psi to get our official normalized wave function as square root of 1 over a cubed times pi times e to the minus r over a. Done. So now on to part D. This problem, or this part of the problem, is basically follows the same steps as the previous, but we can walk through it because the function, or the wave function, is a little bit different. So to start, normalizing, we need our normalization integral. And we have tau this time because it wants it over 3D space. And we can plug in our psi. So we get n squared integrate r squared e. And this 2 is going to cancel out with the square, so we're just going to get minus r over a. D tau equals 1. And now we can just substitute in our d tau, which we talked about in the previous part, and we get n squared 0 to infinity r squared times, don't forget, that's a little tricky. We still have to multiply by r squared, even though we already have an r squared here. So we have r squared times r squared e to the minus r over a dr, integrate 0 to pi sine theta d theta, integrate 0 to 2 pi d phi, all equals 1. So same thing, we're going to solve this integral first, and we use the exact same series solution. So again, that solution is from 0 to infinity, x to the n, e to the minus a times x dx equals n factorial over a to the n plus 1. So comparing these two, we can make the appropriate substitutions. So here, x equals r, and n equals 4 this time. I separated it out so you wouldn't forget to multiply by the r squared, but when you eventually put them together, you're going to get r to the 4th. So we have n equals 4. And then here, we just have a equals 1 over a. A equals 1 over a. So now that we have these substitutions that make this integral look like this one, again, we can just plug in our substituted values for this answer. So we get integral 0 to infinity r to the 4th e to the minus r over a dr equals 4 factorial, we'd plug that in, equals 24, divided by 1 over a to the 5th. N plus 1, we get 5. So simplifying this, we get 24 a to the 5th. All done. Check. So now we can move on to the second and third integrals, which are the exact same as the previous part. You can just plug them into your calculator. Integrate from 0 to pi of sine theta d theta equals 2. And the integral from 0 to 2 pi of d phi just equals 2 pi. Check, check. So now same thing, we just take these answers and plug them back in here and manipulate. So we get n squared times 24a to the 5th times 2 times 2 pi equals 1. Simplifying, we get n squared 96a to the 5th pi equals 1. And then solving for n, we get n equals square root 1 over 96 pi a to the 5th. Similar process, but it still works, and it all comes down to this series being essential to finding that solution, so you don't have to do it the long way. And then in the end, to get our psi, which I'll just do in this little space, our normalized psi is square root of 1 over 96 pi a to the 5th r times e to the minus r over 2a.